Okay, well, good morning, everybody. We're back for the final lecture before the exam on Tuesday. So, as I said to everyone on Tuesday, the plan for this morning is to introduce the material on climate change. And I think this will work well because my plan is to go up to the end of and include basically what I've called how the atmosphere works, right? Before we launch into a discussion on global warming, climate change, whether it's real, whether it's not, all of that stuff, I just fundamentally believe it's important to understand the basics of how the atmosphere works, to be able to explain the greenhouse effect and understand how the atmosphere processes energy from the sun. So we're going to do that for about 30 minutes this morning. This material will be on the exam for Tuesday. And then once we're done that, I will pull up the study guide, talk a little bit about the exam on Tuesday, just reiterate what I feel are the most important concepts for you to be able to cover. Yeah, and then I'll put up the lecture material by the mid-afternoon, something like that. So that's the plan for the day. Anybody got any questions or logistical questions before we get started?
So is all of chapter 6 going to be on the test on Tuesday?
Not unless you want it to be, Keegan. No.
No.
No, that's a big negative from Holly as well. No, so it's just up to today, right, on the exam. I hope I didn't confuse things in that email to you. You know, the schedule is always in a little bit in flux, and Snowbird put that also a little bit behind the 8 ball. So what I've decided to do is, instead of making the tweet due now on climate change, when we will only have covered the greenhouse effect, that's all been pushed back to next Friday, right? So quiz number 4, which covers chapter 6, climate change, and the discussion tweet, all due next Friday. Does that make sense, Keegan? All right, cool. Any other questions?
Thank you.
Yeah, you bet. Anything else before we get going today? All right, cool. Okay, everyone. So let's start here and begin this discussion on what, as I've said, I tend to call how the atmosphere works. And this slide here illustrates one key point, right? And that is that when you look at the constituent gases of the atmosphere, okay? So if you took a weather balloon and you sent it up right now from the surface of where you are up through the lower atmosphere up to the stratosphere, okay? These two gases, nitrogen and oxygen, will dominate any readings that you get back, right? Now, it'll vary as it goes up the atmosphere. In some parts, there will be a little bit more of something than the other, right? You would expect, for example, if you're sending a weather balloon up from Houston, and I know some of you are from Houston, that the amount of water vapor in the balloon will be a little higher than it will be in, Montana. But all things being equal, when you look at the average concentration of gases in the atmosphere, these two gases, nitrogen and oxygen, completely overwhelm everything else, right? The interesting thing, I think, if you're a weather nerd like me, is that from a climate perspective, these two gases are actually pretty dull, right? They don't really do much. I mean, yeah, we need oxygen. Okay, that's important. We got to breathe, and we know that oxygen combines with O2 to form ozone, certainly important. Nitrogen's important for other reasons, right? But in terms of regulating the climate, these two gases don't really do much. Now, the green slice here is other stuff like argon, right, which is a fairly high percentage. But when we take that green slice and we look at other things in it, okay, there's really, really small concentrations of gases like carbon dioxide, water vapor, methane, and other things, right? So CO2, carbon dioxide, and that's a gas that we are going to talk about quite a lot in chapter 6. It's going to be the most important gas that we talk about, right? Carbon dioxide by volume constitutes about 0.041% of your weather balloon, right? Think about that. 78% is nitrogen, 21% is oxygen, 0.041% is carbon dioxide, right? If you were going to express that in terms of how many parts per million, so if you take your weather balloon and you fill it with 1 million parts or 1 million little Lego blocks, right? What I'm getting at here is rounding up, about 780,000 of those Lego blocks would be nitrogen, about 210,000 would be oxygen, and only about 410, right, would be carbon dioxide, okay? Random question, are we having class Saturday? Not unless you want to. No, I've just decided, Chinera, thanks for that. It's a good question. I'm not doing a makeup class. What I decided to do is upload the lectures on natural gas and nuclear for your interest only, and just leave it at that. Okay, so I hope that addresses that. There's no class on Saturday. All right.
I have a quick question.
Holly.
You said that carbon dioxide was 0.041%, but when converted to parts per billion, it's
no, parts per million.
Million. Okay, thank you.
Yeah, it's about 410, right? So the point simply here, and this is a key point, right? When you look at the volume of the atmosphere, carbon dioxide by volume is very, very small, right? It's way less than 1% of the air by volume. What else is in there? Well, water vapor is in there, right? Water vapor varies, okay, near the surface of the earth. And if you're in Houston or if you're in Louisiana, water vapor can be 1 or 2 or 3%, which means that there has to be a little less nitrogen and oxygen and other stuff. But water vapor is generally less than 1% as well, right? My point, everybody, is that these gases like carbon dioxide and water vapor and others make up a tiny fraction of the volume of the atmosphere. That's just a single point I wanted to start this conversation. Does that make sense to everybody? Right? So why do we talk about CO2? Why is carbon dioxide such a significant gas when it comes to this chapter? Anybody want to have a stab at that? If it only takes up 410 parts per million, Holly, why aren't we just going, let's forget about it? Anybody? Why are we going to get bent out of shape about CO2? Or at least I am. What do you think?
I don't know like specifically, but like I remember learning about methane and how it's kind of like, I don't know. I don't want to say it. Sorry.
No, go for it. I love it when you just step out of that comfort zone and go for it. That's far better than not. So
I feel like I'm gonna like trip up on my words, but I remember learning like about methane and how it's one of the greenhouse gases, but it allows like the solar radiation, it just stays trapped because it like reflects back into Earth. And that's why it's like one of the most dangerous ones.
Okay, so you didn't trip over your words there. That's pretty close and quite well explained, right? So I didn't do methane justice, or methane as we say in Britain or South Africa. I haven't done it justice because we skipped natural gas as part of SNOVID. But yeah, methane is that's what natural gas is, right? And you mentioned that word greenhouse gas, and you mentioned trap. I'm glad you used the word trap, right? Because we're going to talk about that in a second. So it's a greenhouse gas. Is carbon dioxide also a greenhouse gas, do you think? Has anybody heard that as being a greenhouse gas? Yeah, all right. So what does that mean? Who wants to have a stab at that? I don't want to keep picking on Holly, because Holly and Keegan are always number 1 and 2 on my Zoom screen. You've drawn the short straws here. So someone else.
I know that like greenhouse gases like occur naturally.
Okay.
So like it keeps our Earth at a temperature that's like suitable for life.
Perfect.
I believe.
Perfect. You believe correctly, Sunny. Thank you. Can you think of a greenhouse gas? So, okay, awesome. Is carbon dioxide a natural gas? Or is it a human-made gas?
Yes, it's natural.
It's both, right? Okay, yeah. Photosynthesis, plants take carbon dioxide out of the atmosphere, right? As part of the photosynthetic process. Anything else? Can anyone else give me a natural greenhouse gas, do you think, besides carbon dioxide?
Hydrogen?
Hydrogen doesn't do much from a greenhouse perspective. But what happens when hydrogen joins up with 2 oxygens?
Oh, isn't that water?
Yeah, water vapor, right? Water vapor is a greenhouse gas, okay? So we're going to talk about greenhouse gases here for the next little while and explain what's going on, right? So how does the atmosphere work? How does our climate work in 20 minutes? I mean, talk about not doing this justice, right? Because if we're going to talk about climate change, then how does climate work, right? And I suppose the big question here, and it's a theme that I've tried to raise several times and will continue to, especially when we look at things like biodiversity, right, is our global climate changes naturally and it changes independent of human beings. How do we disentangle that from anything that we might be doing to it? Okay, so here's one way of looking at this. So this little diagram shows this beautiful blue blob. This is planet Earth. And planet Earth sits out there in space and receives energy from the sun, right? It receives radiation. Okay, everybody see that? Cool. So we're getting energy from the sun in the form of radiation. That radiation travels through space in the form of waves, right? Like waves in the ocean. And they have a crest and a trough and a crest and a trough, right? And some of those waves come to us in very, very short waves, right? They look like ziggy little heartbeats. And some of those waves come to us in the form of very long, lazy waves. The point is the energy is carried in those waves through space in the form of incoming solar radiation, sunlight, right? Radiation, okay? So the energy travels, so those are the orange arrows. So the sun, this huge nuclear explosion, sends out all of this radiative energy through space. And all of the planets out there are interacting with that energy. And our Earth is too, right? So that energy begins to move into the atmosphere of the Earth. And what happens? Well, the Earth warms up because of that energy, and the Earth itself starts giving energy off. So that's the first fundamental law, right? It's the first law of thermo, is every object on this planet is giving off radiation. As you sit at your desk right now, everything around you is giving off radiation. Every single thing is, okay? And the hotter the object, the more radiation it's giving off. So you probably don't feel the radiation coming from the pen or the radiation going off the top of your head, the radiation being exerted by everything around you, because it's just incredibly small amounts. But the hotter the object, the greater the energy, right? So we get this huge amount of radiation coming in from the sun, and the Earth heats up, and the Earth gives off that energy back to outer space. That's what the blue arrows are showing, right? Everybody with me there? And we can describe that relationship between the incoming radiation from the sun and the outgoing radiation from the Earth by this little equation. Okay, so what's this little equation? This little equation here is called the continuity equation, right? And the continuity equation is written as input minus output equals delta S. I don't know, Siri. Siri keeps trying to answer my questions. I was playing golf the other day, and every time I hit a bad shot, I was like, oh, darn it. And Siri would go, I'm sorry, I cannot help you with that. I'm like, well, duh. All right, so let's see if we can keep Siri quiet on my watch here for a minute. So that equation is input minus output equals delta S, okay? So the input here, everyone, is the energy from the sun. The output is the energy that's being given off by the Earth. Does that make sense, right? So the input is incoming radiation, and the output is is the Earth energy coming back to space from the Earth. What's delta? Delta is change, right? And S is the storage of energy, right? The change in the storage of energy within the Earth atmosphere system. Does that make sense? Think about it. I try and impress this upon my wonderful young son. If you look at your bank account and you apply this equation to your bank account, the input is your paycheck. The output is your spending habits, right? Delta S is your bank balance, right? So if you're earning more than you're spending, then delta S is increasing, and you probably want that rather than spending more than you're earning, okay? Does that make sense? So in terms of climate here, delta S represents the global climate, global temperature. We're putting energy into the system, and the Earth is emitting energy back to space. Delta S is the change in the storage of heat energy represented by temperature or climate. So let me stop there and make sure everybody's up to speed. Does that make sense to everybody? All right, cool. Now, here's something that might surprise you or maybe even blow your mind. So assume for a moment that we have no atmosphere wrapped around the Earth, none. There's no atmosphere sitting around planet Earth. And it sits out there in outer space, right? And it's absorbing energy from the sun. It's absorbing energy from the sun. The surface of the Earth, there's no atmosphere. The surface of the Earth heats up and it starts giving off energy. And we just let that situation settle down for a little while, right? We let that settle down. The temperature of the surface of the Earth, right, if that was the case, would be minus 18 degrees Celsius. Minus 18 degrees Celsius. That would be the average temperature of the surface of our planet if we didn't have an atmosphere. Now, some of you may be going, wait a minute, I don't understand that. There's no atmosphere. We're getting all of this energy from the sun. Yes, you are. All of this energy from the sun is coming in, and the Earth is heating up and giving energy off, right? That is known as our equilibrium temperature. That is actually what the temperature of planet Earth should be without any atmosphere. In other words, think about Snowvid last month, and the wind chills there are minus 25. That's what our temperature on our planet should be, bizarrely, okay? But it's not. Why isn't it? It's not because we have this thing around the Earth called the atmosphere. And what happens is there are gases in that atmosphere that do something with the energy coming in from the sun and something with the energy being given off by the Earth, right? Does that make sense, right? By putting that atmosphere around the planet and having gases that we call greenhouse gases in the atmosphere, that keeps our planetary temperatures not minus 18 degrees Celsius, but it makes our average planetary temperature positive 15 degrees Celsius on average. Now, some parts of the planet are obviously much warmer and some are much colder. So that's an average global temperature. If you like Fahrenheit, that is about 62 to 64 degrees Fahrenheit on average. Okay. In other words, and this is a key issue, there is a 33 degrees Celsius temperature swing just because of the atmosphere. Okay. Makes sense to anybody? Everybody? Right? Okay. So these gases in the atmosphere, like carbon dioxide and like water vapor, these greenhouse gases, are fundamental to life on Earth. If we didn't have them, we wouldn't be here, right? And I'm going to explain that in a bit more detail in just a second. Okay. So look at this. When we look at the amount of energy coming in from the sun, right, that strikes the surface of the Earth, and then we look at the amount of energy being given off by the Earth. So if you go to any spot on the Earth and you measure the amount of sunlight that's coming on that spot and the amount of energy that's being emitted from that surface, anywhere on the surface of the Earth, right? That is what this map shows. This map is showing, it's a really important map again. It is showing the net radiation, right? The net energy that's left over, looking at that input minus output, all right? Just at any spot on the surface of the Earth. This just happens to be for March. It's an average for March. And I want you to look at the scale here, everybody. And the numbers aren't critical. What is important here is that everything that is yellow and red has an energy surplus, has too much energy, right? Has a positive energy balance. And anything that is blue has a negative energy balance, right? Does that make sense to everybody, right? Okay. What do you notice? Anything in yellow and red is positive. Anything in blue is negative. What do you notice? And this is March, right? So March, the sun is directly overhead over the equator, and the equator is right there, okay? Question from Teresa, is net radiation the delta S in the input-output equation? So Teresa, that's a great question. In this instance, it is. Let's assume that it is, right? There's other things going on, but we won't complicate that. So that's a great question. So the delta S is the net radiation, the energy surplus. So what do you notice? So then the closer it is to the equator, the hotter it is. Yeah, makes sense, right? The more energy excess there is, right? This is the March average. So for the whole month of March, the tropics, right? So if you think about the tropics being sort of 10 degrees either side of the equator, and the subtropics, sort of 30 degrees either side of the equator, they're always in an energy surplus. And the polar regions, North Pole and South Pole, is always in an energy deficit. Right? So what does that mean, everybody? What's the implication of this diagram? Does it mean, let me nudge you along. Does this diagram mean that the tropics are getting hotter and hotter and that the poles are getting colder and colder? Are the tropical regions starting to overboil and the polar regions are starting to freeze themselves shut or not? Holly, you're looking skeptical. Your head's going left and right. Anybody else?
Wouldn't it kind of balance each other out a little bit because of the Earth's constant tilting back and forth during the year? And then like, well, I learned in geography about like, what is it called? Gosh, I just totally escaped me.
Continentality?
But like there are like trade winds that move the like that carry like the heat from the ocean up and down, and that's why we have seasons. That's kind of what I learned.
The Gulf Stream thing, right?
Yeah, Betty?
Yeah, the Gulf Stream, I think it is, or yeah, it's the winds that carry the warmer winds to like Europe.
That's exactly right. Okay, so the tropics get warm and the poles are cold. And the tropics go, you know what, I've got too much heat here. So I'm going to send out warm winds and warm ocean currents to the poles. And the poles go, that's cool. I'll send back my cold ocean currents and my cold winds towards the tropics. There is this continual, ongoing, never-ending game of pass the hot potato between the tropics and the poles, right? That never balances out. The tropics never get to a position where they go, okay, awesome, my delta S is 0, and the poles go, well done, tropics, my delta S is 0. Never happens, right? The tropics are always in an energy surplus, which is why they're warm. The poles are always in an energy deficit, which is why they're cold. But the reason why it doesn't boil up and the poles don't freeze over is that there is this continual movement of heat energy in terms of warm ocean currents like the Gulf Stream, right? And cold ocean currents and warm air and cold air, which is why, if we go back to our lectures on Tuesday, which is why the chlorine nitrate and the hydrogen chloride, right, those reservoir gases get transported to the poles, because all of those air particles get transported to the poles by the upper level winds, right? And Holly, you just said something that sort of prompts me to go to the next diagram. That is a snapshot in March, right? But look what happens seasonally for a second. Okay, I'm going to put this in motion, and it should be in motion. Is that moving for you guys? Okay, so just look at this. I'll let this run for a second. August, September, October, November, December. Anything in orange is a surplus. Anything in blue is a negative. What do you notice? July, August, September, October, winter. Just look at North America. Middle of winter, spring, summer, stinky summer, right? There is this continual shifting, moving north and south because of the tilt of the Earth. If the Earth wasn't tilted, this map would not move. If the Earth wasn't tilted, the tropics would be permanently orange and the poles would be permanently blue. But because the Earth is tilted and it goes around the Earth, right, once every 365 so days, okay, this is exactly what causes seasons, what you see right now. It's the seasonal shift in where the sun is directly overhead. Now it's directly overhead at 23.5 degrees south. Now it's overhead at the equator. Now it's overhead at 23.5 degrees north. Does that make sense? Right? So just I use this just to show that energy is not static. Okay. All right. Now we come, how are we doing on time? We're doing okay. Now we come to the big one, right? So this is where we start looking at the radiation budget and the greenhouse effect. All right, so this is the electromagnetic spectrum, everybody. Super, super important. I'm going to give you the electromagnetic spectrum in the exam, right? So what is the electromagnetic spectrum? The electromagnetic spectrum captures the energy, the entire range of energy that comes to us from the Earth and from the sun, right? So what are we looking at the bottom here? We're looking at the bottom. I need to have the annotation tool on here. Right, so we're looking at the bottom here is the wavelength, right? So the wavelength is the distance between the crest of two troughs, right? And we've just got an intensity here on the axis with no numbers, okay? And the two key areas of this, right? So this is the sun's energy spectrum, and this here in red is the Earth's energy spectrum, okay? And you can see here as you move on this screen from right to left. So look at radio waves. Radio waves are the longest wavelengths, right? So if you're tuning in to KTCU 88.7, that signal is coming across radio waves, and those wavelengths are about 1 to 10 centimeters, right? They're not very long, okay? And if you get hungry and you want to heat something, you pop it in the microwave, right? The microwave is zapping your food with microwaves, right? And those wavelengths are about 1 millimeter, very, very, very short wavelengths. And as you start moving down that energy spectrum, the wavelengths get shorter and shorter and shorter, okay? The next one down here, everybody, is infrared, right? So this is infrared over here. And infrared, these wavelengths are in microns, right? So 10 microns, 1 micron, incidentally down here, 1 micron, that is 1,000th of a millimeter. You can't see it with the naked eye, okay? That's all infrared energy. And then we get into this important part of the spectrum here, which is visible light. Visible light is a very, very, very small part of the spectrum, 0.4 to 0.7 microns, okay? But look at this huge bubble that the sun gives off in that visible light. And then we go down to ultraviolet over here. Remember ultraviolet A, ultraviolet B, ultraviolet C, okay? So the electromagnetic spectrum tells you where we're getting our energy from. Now, there's one thing I want to point out, and then I'll stop, because I know there are going to be questions. I hope there are questions here, right? The one thing I want to point out here, everybody, and it's also critical, is that the Earth's spectrum here has been exaggerated about 100,000 times. If you were to plot the Earth and the sun on the same scale, you couldn't. You would either not see the Earth, or the sun spectrum would shoot through the ceiling, right? So we've just exaggerated the Earth here about 100,000 times, just so you can see it. So just based on that, everybody, what can someone say? Someone just summarize what's going on in terms of the energy we get from the sun versus the energy we get from the Earth. What can you say generally? Someone give me a quick 15-second summary of Earth energy versus sun's energy. What would be your
attempting
answer
to compare like the sun to the Earth is kind of not a good balance, really. You can't really set them on the same balance of terms.
Right?
Yeah.
Right. You can't set them on the same balance. And then, of course, if you were to summarize the energy given off by the sun, the energy that's given off by the sun is dominated, right, by ultraviolet, visible, and this part of the infrared spectrum here. Whereas all the energy given off by the Earth is infrared energy with a little bit of microwaves, right? We fundamentally have a different type of energy. I mean, it's not a different type, it's still radiation, but they're very different, right? And as you start moving here towards these longer wavelengths, the amount of energy that's carried on those photons is small relative to the sun's energy, right? So the sun's energy gives you ultraviolet, visible, and near infrared, high energy, short wavelengths. The Earth energy is lazy long wavelengths, all in the infrared spectrum. Need everybody to understand and appreciate that. And on the next one here, I've just got another look at the electromagnetic spectrum, right? I've just kind of redrawn this, showing you've got visible light here between 0.38 and 0.78, right? Here's your UV, A, B, and C, okay? And here's your infrared. And as you move to the right here, the wavelengths get longer and the energy gets lower. Or as you move to the left, as you move to shorter and shorter wavelengths, the wavelength gets shorter and the energy increases. Okay, Keegan, question. The sun has short wavelengths and the Earth has long wavelengths. So the energy from the sun is incoming solar radiation. And we generally refer to all of that as shortwave radiation. The Earth, the energy that's given off by the Earth is long wave radiation, right? Infrared long wave radiation. Everybody with me? So when we go and just look at this part of the spectrum here that has UV, this was the environmental issue that we talked about, right? UVA, UVB, UVC. This is all incoming shortwave radiation that is absorbed, right, by ozone in the stratosphere. Most of it gets the UVC is taken care of. A little bit of UVB gets through, and quite a bit of UVA gets through. That is all occurring on the left-hand side of the spectrum, to the left of visible light, right? All makes sense. Any questions on that? Okay, now, the final one. All right. This is a gigantically important diagram, right? If I was a betting person and I was headed to Vegas weekend, I would put everything on red that you will see some form of this diagram on Tuesday, right? Why is it so important? Because this diagram explains the greenhouse effect, okay? It explains the greenhouse effect. All right, so what are we looking at here? So let me just take this a little more slowly through here and really make sure that everyone's happy with this, okay? And I'm going to change colors here so we can see something a little better, right? So I'm going to do, let's do this dark green. Okay, so we're looking at, let's look at the top diagram. This top curve is the energy emitted by the sun, and the blue curve is the energy emitted by the earth, okay? And instead of exaggerating the earth 100,000 times, as you can see in the top left-hand corner of the diagram here, I've shrunk down the sun by 1,000,000 times, factor of 10 to the 6, right? So even though Gavin correctly said you can't really compare Earth and the sun next to one another because it doesn't really work, here we're doing it, Gavin. We're comparing them, but I've shrunk the sun down side by side, okay? Everybody with me? Please, folks, if this doesn't make sense, just interject. It's such an important diagram. So the top of the red curve is the energy emitted at the sun's surface. The top of the blue curve is the energy emitted by the Earth's surface, right? And you can, and on the bottom here is wavelength. So this is visible, and this is all infrared down here. All right. The red shaded area, this red shaded area here, is the sun's energy that is absorbed at the Earth's surface. So the energy comes through space, it passes through the atmosphere, it goes through the atmosphere, it goes through the atmosphere, and it strikes the Earth's surface. Everybody with me? That's the sun's energy absorbed at the Earth's surface. So what is the missing white part here? I can't hear. Who's that? Vin, I can't hear you. There's something up with your microphone. You can put it in the chat or someone else chime in. What's the white part here? Okay, Vin said it's UVC. Hang on to that for a second. If this is the energy emitted by the sun, and this is the sun's energy absorbed at the Earth's surface, what's the missing white part? Where's that?
Is that the change in S? Is that like the equation?
It's not the change in S. Keep thinking.
Is it a portion of energy blocked by the atmosphere that doesn't reach the Earth's surface?
Bazinga. It is. Nelia, good. How do you pronounce your name? Nyla? Nyla?
Neela.
Neela. I apologize. Thank you. Yeah, that's exactly right. Okay. That's the sun's energy that comes to the top of the atmosphere and never makes it to the surface of the Earth. So where does it go? It's absorbed by the atmosphere. And now to move on from Vin's comment in the chat, what is that energy absorbed by? Vin, you are correct. It's absorbed by stratospheric ozone. Not just UVC, but the ozone is absorbing those wavelengths. Does that make sense to everybody? Now let's look at the Earth, right? This is the energy that's, and then I'll explain the bottom diagram. This is the energy that is given off at the Earth's surface. Okay, it's all long wave infrared radiation. This in blue here is the Earth's energy that's given off that escapes directly to outer space. We call that the atmospheric window. It's not really a window, but you can think of it as the atmosphere saying, hey folks, we're going to open up a window here and let that energy escape. So it's the energy given off by the Earth that escapes directly to outer space. So what's all this white area here? If you can explain to me what the white area here is, you totally understand this diagram. What's the white area here?
Is it the energy that the atmosphere and the greenhouse gases reflect back onto the Earth's surface and keep trapped?
Exactly, right? Exactly. Sunny, Ari, perfect, okay? Energy trapped by the greenhouse gases. Now, I'm glad you're all using the word trapped because that's incorrect, but let's think of it like that. So the Earth gives off energy, which is the blue curve. Some of that energy escapes directly to outer space, which is the atmospheric window, but there are gases in the atmosphere, like carbon dioxide and water vapor and methane, that they see that energy coming up from the Earth and they go, oh, I'll have some of that, please. Thank you very much. I'll take some of that long wave radiation. And those gases absorb that energy. Okay, so anything in white here is energy given off by the Earth that's absorbed by the atmosphere. Anything in white here is energy that is given off by the sun, but is absorbed by the atmosphere. Does that make sense to everybody? Right?
Wait, sorry. So the blue, it's also absorbed by the atmosphere?
No.
I mean the white part.
Yes. Anything in white here is absorbed by the atmosphere. Right? Okay. The bottom part of this diagram, I've got to keep an eye on time because I do want to talk a little bit about the exam. The bottom part of the diagram shows you the wavelength along the bottom. And then it's got this vertical axis that is absorption from 0% to 100%, right? And what we're going to do is we're going to move left from the left-hand side here, in other words, from 0.2 microns, which is ultraviolet, right, UVC. We're going to move to 0.3 to 0.4, all of that's UV. Then we've got the big rainbow there, which is the visible spectrum. And then we're moving into the infrared, right? And what this shows you is the percentage of absorption by the atmosphere as you move across that spectrum. So let's just take this part here, right? This part here in green that I've highlighted right here shows that 100% of the energy, in other words, 100% of all of this 0.2 to 0.3 micron energy is absorbed by the atmosphere. What's doing that? How's that happening? 100% of all of this is absorbed by the atmosphere. Sunny, what's absorbing that?
Isn't it the stratospheric ozone?
Bingo, it's the stratospheric ozone, right? That is absorbing 100% of the UVC, a little bit of the UVB, and then look at this. This white area here, it lets in almost all of the UVA. The absorption goes down to almost zero. Everybody see that? Then we move through the visible spectrum. There are some gases that absorb a little bit of it. And then we get to this really funky part of the spectrum here, where gases in the atmosphere now start selectively absorbing at certain wavelengths only, right? In other words, when you get to this part of the spectrum here, right over here, there are gases in the atmosphere that say, I'm going to take 100% of that little bit of energy, and then I'm useless here, right? And then it gets really close to 100%, and then I'm useless again, right? Does that make sense? These gases in the atmosphere, everybody, are what we call selectively absorbing the energy given off by the Earth. The gases like carbon dioxide and water vapor and methane and so on, okay, are selectively absorbing energy given off by the Earth. And what I'll do on the next image here, so anything in orange here, all of the orange is all of the gases in the atmosphere combined. But let me put on water vapor and carbon dioxide, and you'll see what happens here, right? So here's water vapor and carbon dioxide. I'll go back one. There's all the gases. Here's water vapor and carbon dioxide, right? Water vapor is a very important, very powerful greenhouse gas. And water vapor starts selectively absorbing energy, right? Right over here, water vapor starts taking out a little bit there and a little bit there, right? And quite a bunch there. and a whole bunch there, right? And a whole bunch there. Do you see that? Water vapor gets a little bit there and a little bit over there, okay? Carbon dioxide is pretty good over here and really good over here. That makes sense? So what you can see on this diagram is that if you look at the top part of the diagram, right, all of these areas here that are in white that represent absorption in the atmosphere match these vertical peaks here that show where that absorption is occurring and by what gas. And this big white area here is dominated by water vapor. This big white area here is dominated by water vapor and carbon dioxide. Does that make sense to everybody? What you're looking at is the greenhouse effect. You're looking at the gases in the atmosphere that begin to absorb energy and thereby warm the planet. They don't trap it. I know everybody, and I'm glad you used that term trap, right? People think, well, carbon dioxide and water vapor acts like a blanket, all right, and traps the energy. That's not even how blankets work, and it's not even how greenhouses work, okay? What really happens is these gases absorb energy, and therefore they heat up the atmosphere and emit energy back to the surface. That's the greenhouse effect. And if you're struggling with this diagram, right, think of this. What happens if we took all of the gases out of the atmosphere, right? Let's remove all of those gases out of the atmosphere. Totally. What would this top diagram look like if there were no gases in the atmosphere and our global temperature was minus 18 degrees Celsius, that comment we started with? If you can answer this question, you're good to go.
Wouldn't there be no, oh, sorry.
Go ahead. Go ahead.
Go ahead, Keegan.
Wouldn't there be no white areas? Because the white areas like are equal with like, because like the white area and the blue is equal to the water vapor, like the
Yeah.
blue area. I'm not good at explaining that, but
Yeah, no, you got it. Vin put that as well in the comment. There will be no white area. You take the gases out, there's no white area. Nothing. In other words, under the red curve, it would be all red. All of that sun's energy would be absorbed at the surface of the earth. There'd be no stratospheric ozone dealing with any of it. There'd be none of these shenanigans down here with stratospheric ozone in the orange, okay? And then the earth would heat up. And what would the earth look like? The earth would be completely covered in blue because that atmospheric window would fill the entire curve under the earth. And all the sun's energy would escape back to outer space. And our global temperatures would be minus 18 degrees Celsius, right? What we start doing is we start putting these gases into the atmosphere like water vapor and carbon dioxide. A large part of that is natural, okay? And suddenly our planetary temperatures go to positive 15 degrees. And the environmental issue, and the reason why we look at carbon dioxide and other gases is that humans, of course, are adding carbon dioxide to the atmosphere, right? Even though it's a tiny fraction of the volume of the atmosphere, right? So remember, everybody, less than 1% of the gases in the atmosphere are these gases like CO2 and water vapor and so on, less than 1%. And yet they play such a ridiculously disproportionate role in keeping our planet warm. And this is the summary diagram, right? This is the greenhouse effect. So the greenhouse effect on the left shows sunlight coming in, and some of that is reflected off the surface of the earth. Some of it is reflected off clouds. Some of it is absorbed by the atmosphere. The bottom line with the greenhouse effect when we get down here is that about half of all the sun's energy makes its way to the surface of the earth and warms up the surface of the earth. Some of it, the rest of it is absorbed by the atmosphere or just simply reflected, okay? And then the earth starts giving off radiation, but because we've got these gases in the atmosphere, like the greenhouse effect, that energy is emitted back towards the surface of the earth. Take those gases out, there's no white area, we freeze to death. Put the gases back in, we start ramping up the greenhouse effect. Does that make sense to everybody? It's complicated, right? But it's critical to understanding how climates change and the impact that humans are having on the carbon cycle. All right, I'm going to stop there and see if there are questions. And then I want to just make some comments about the exam. Comments.
I just have like a random question.
Fire away.
In lecture on Tuesday, you talked about the ozone hole over the South Pole. Is that kind of what would happen? Like, since there's a big hole, is that the type of climate we would see if it continues to enlarge?
Yeah, so that's a really interesting question, and it's not a random question. So that's an interesting one, right? Because if the ozone is thinning, right? So if we go back, I'm actually going to go back here. If the ozone is thinning, okay, then more of that energy is coming through, right? Down on this left-hand side of the diagram. Does that play out and change climates? Not really, because even though it's high energy UV rays, it's so specific to one particular area, and overall it's a very small component of the greenhouse. It's a really great question. That doesn't really play into climate. The question from Cole, yeah, is this lecture going to be posted on D2L to review later? Absolutely. So Cole, what I'll do this afternoon is post all of the lectures of the week. Any other questions on this? Oh, let me just scroll up a second. Aubrey, in a perfect world, what would the balance be between the gases in the white? That's a great question. In a perfect world, well, it depends, right? I don't know what a perfect world is. If you want to grow fantastic wines in Scotland, then we need a few more greenhouse gases to warm the temperature in Scotland and make it more look like France, okay? It depends on what your idea of perfect world is. That's a difficult question to answer, Audrey, because we've got 8 billion people on the planet, and perfection to some is, I mean, many would argue we're in that Goldilocks world right now, right? With 100 years ago, with a temperature of 15 degrees Celsius, that's great, right? And, you know, if things warm by another 2 degrees Celsius, does that change the world from perfect to imperfect? Well, that depends if you're living in the Sahara or not, right? I really can't answer that, but it's quite an interesting question. Anything else on the questions? All right, awesome. So let me stop that and let me just go to this. So let me share my, all right, just really quickly. So I've posted the review. You're now used to the type of exams I've set. There's slightly fewer questions in the exam on Tuesday. I think there are 33, right? There's about, I think it's out of 45 points, and about 10 to 12 are written, okay? And the written ones will be no surprise, right? The written ones are all somewhere on this study guide. So if, you know, again, if I was to put some money on it, I would probably really understand how stratospheric ozone is formed and destroyed. Clearly, this is going to be a question, everybody, right? This one over here, the recipe for ozone loss over Antarctica. Right, I said that. I want you to be able to explain why ozone is destroyed as rapidly as it is, where it is, okay? And as I said, I'm happy to meet with you individually, and I'm happy to be available on Sunday and Monday to explain that. So that's an important one, right? As is this little bit today, the electromagnetic spectrum. Please don't go and learn the electromagnetic spectrum off by heart. I don't expect you to know what the wavelength of UVC is. I'm going to give you that. I'm going to give you the picture, either the one that I just showed you or some version of the electromagnetic spectrum. And I'm going to ask you some questions on that, right? And another important one is this one here, factors that govern pollutant concentrations geographically, right? So if I give you a map and say, look at this map of the US, and these are the counties that are struggling when it comes to stratospheric ozone, tropospheric ozone or carbon dioxide or whatever the pollutant is, explain why. Right? What's going on there? And you also need to be able to calculate how many houses a wind turbine can support. Those are big. Those are big, big, big. So questions and thoughts or comments? And how are we doing on time here? It's 11:48. I am happy to hang around now. Again, please, everyone, I'm happy to set up individual appointments with you. Don't feel like you're bugging me or impinging on my time. I'm happy to meet with you. And I should be available, or at least all of Sunday and almost most of Monday to answer those questions that as they crop, right? Let me just quickly look at the chat here. Same format as last time. Yep. Genera, 30 questions, 45 points, 33 questions, 45 points, I think, is what it's at. So there's a bunch of multiple choice and then there's these short answers at the end.
Do we need to email you if we have extended time on our tests?
I have transcribed all of the accommodations from last time to this time as well. So everybody from last time is in this time. You mentioned in an email you'd be posting a review or video. Did I read that wrong? No, you didn't read that wrong. I was going to do that, but what I was going to post was basically what I've just covered there, Sunny. Just a quick review of the study guide, and I figured what I'll do is just make myself available in case there's questions that come along. Can we have until midnight to take the exam on Tuesday? No, you got to take it in class, I'm afraid. It's a synchronous exam. I'm just reading off questions on the list.
I have a question. So
Yeah.
how many houses a wind turbine can power? Like, is there a page in our book, or is that something on a PowerPoint?
Let me pull it up for you real quick. Give me 1 second. All right, let's see. I should be able to find that energy for renewables. It is going to be this slide coming up in a second. Gavin, give me another. There it is. It's this one here. Can you see that, Gavin?
I don't know why I just forgot.
No, that's all right. So I think most people kind of really overthink this question, and I get pages of discrete calculus here. So I've got to give you the information. I've got to give you what is the size of the wind turbine. So let's say it's a 1.5 megawatt wind turbine. I'll say this is how many hours are in a year. I think it's either 8,750 or 8,760. It doesn't really matter, right? You multiply the rating by the number of hours in the year. That tells you how much energy a wind turbine could produce. You multiply that by the capacity factor to tell you how much energy it is producing. And then you just divide that by the consumption on a household, and that tells you how many houses it can support. All righty, so I'm going to hang around. So let's fire up those questions, young environmentalists.
Just to repeat what you said, you said multiply the rating by what?
By the number of hours in a year.
Number of hours in a year.
Yep.
And then you multiply that number by the capacity factor, and you divide it by the consumption of each. Oh,
What the average consumption per household is. That's exactly right. So if it's a 1 megawatt wind turbine and it's producing 1 megawatts for every hour for a year, you multiply 1 by 8,760, right? So it can produce 8,760 megawatt hours of energy. Let's say it's just operating at a 10% capacity, right? So instead of 8,760, you multiply that by 10%, that'll give you 876. And then just divide that by the consumption on the house.
will it ever be like a negative number, or will it always be a positive one?
If it's a negative number, then I'd suggest you don't build wind turbines anywhere. It's going to be a positive one, right?
Okay.
And so that's an interesting question. Ask yourself, does my answer make sense, right? If you've got a wind turbine and you calculate that it's going to support 0.0173 houses, then you probably made a mistake in the calculations. Or if you tell me that a wind turbine is going to support 8 billion houses, then well, that's great, but it's tricky. So give yourself a what sort of makes sense. 2, 3, 4, 5, 6, 700 houses, somewhere in there. Yeah.
All right. Thank you so much, Mr. Slattery.
You bet. Have a great day.
You too.
Thank you, Dr. Slattery.
Have a good one.
Thank you.
Yep.
Thank you. See ya.
You bet, Madeline. Fire away, Vin. Oh, that's a good question, Vin. The blue part is the energy that the Earth is emitting that is not absorbed by any gas in the atmosphere. So that's why we call it the atmospheric window. So it's in a very specific set of wavelengths that get emitted, and there are no gases that can selectively handle those wavelengths. So they escape directly back to outer space. It's not the net storage of energy. Does that make sense? Oh, okay. No, it's just Earth energy. The atmospheric window is Earth energy, just terrestrial radiation. Let's see, am I seeing it? Okay, I saw that, Ben. Thank you. You have a great day too.